Hi girls. So this would be lesson 4 on geometry 1, which is parallel and perpendicular lines, okay? So have a think about, first of all, what do you know about parallel and perpendicular lines? Where would you see them? What's the difference between them? A few of those things. So we won't need to go through measuring angles. That just comes up again. Parallel lines, right? So let's look at the line MN and OP. Why are they parallel? What does it mean? Where would you come across them outside? Have you seen them like as you're walking in your daily walk? Do you know, at the moment you're getting out maybe in a bit of sunshine? Is there any parallel lines that you come across? If you look around your room at the moment, have a look. Pick maybe 5 sets of parallel lines that you can see in the room that you're sitting in at the moment. Right, so let's take down the definition then for parallel lines. Parallel lines are two lines which never intersect. Okay? We say that two line segments, okay, are parallel if the lines that they lie on are parallel, right? So as part of this line here, you could have a line segment. As part of this line here, you could have a line segment. If line 1 is parallel to line 2, then we write it as 1 being parallel to 2. Now that symbol there is really important to take down, right? So you need to be taking these points down as you're going through this PowerPoint. So stop it as you can. So this symbol here, parallel. So line 1 is parallel to line 2. That's exactly. And sometimes they might just write that and you have to know that that's what it means, okay? When two line segments DC and AB lie on parallel lines, we write this as DC being parallel to AB, right? Now remember, we use the square brackets for line segments. We use the straight lines for lines, okay, or lengths. But DC has straight or square brackets here to show that it's a line segment. So when two line segments DC and AB lie on parallel lines, we can write them as DC being parallel to AB. So you see that symbol again. So examples, line 1 and 2 below are parallel. Okay, so at the left-hand side, we have line 1 and line 2. What you notice as well, and that either side of a parallel line is arrows to show that they continue on. We also have line MN and OP. They're parallel. Lines in a plane, or are they parallel? Look at these lines here. We use an arrow heads to show that the lines are parallel. Parallel lines, another keyword that you've maybe never come across before, is that parallel lines will never meet and they're equidistant from each other, okay? Equidistant from each other means that like the space between here and here is the same between here and here is the same between here and here, right? So they're equidistant apart. We can say that parallels are always equidistant. So where do you see parallel lines in everyday life, right? So have a think of that as well, as I explained already. Perpendicular lines then, right? So let's take down this key point and a heading and one of the diagrams. Perpendicular lines are lines that are right angles or 90 degrees to each other, right? So see this line here, perpendicular to this line here, right angles on either side. Same with here. This line is perpendicular. It meets the line AB meets the line CD at this point here, and there's right angles on either side. Perpendicular lines. What is special about the angles at the point of intersection here? Okay, so what is special about those angles here is that they're 90 degrees. So A is equal to B is equal to C is equal to D, and each angle is 90 degrees. And we show this with a small square in each corner. Okay. Lines that intersect at right angles are called perpendicular lines. So let's look at horizontal lines, right? So you would know what horizontal line is. Think of horizon. Horizon goes across the way. So a line that is parallel to level ground is called a horizontal line. So again, look around your room that you're in at the moment and think about, or even on your walk today out in the sun, have a look. Is there any horizontal lines that you come across? So they go straight across. So like this line here is like, I suppose, a graphic, and then this line here is like your walls outside maybe, or you might have a wall inside your house that has bricks like that. Then vertical lines, right? How do we spot vertical? Vertically, right? They go down. So a vertical line is a line that is perpendicular to the horizontal. Okay, so like this, or you could have some wallpaper that'd be like this, going straight down. The next thing that I'm going to introduce you is to axioms. So there's 4 axioms that you have to know in first year. And what is an axiom? Okay, so this is something that you definitely wouldn't have come across before. So the first thing I want to take down is what the definition of an axiom is. So an axiom is a statement that we accept without proof. So eventually when you continue on into your second year and third year maths, you will be doing like theorems and proofs. But an axiom is a statement that we accept without proof. We don't have to prove it, okay? So axiom 1, and you need to take down all 4 of these, okay? Axiom 1 is called the 2 points axiom. And what it is the statement that there is exactly 1 line through any 2 given points, okay? So in reality, you can't draw a line through 1 point. It has to have at least 2 points. So there's exactly 1 line through any 2 given points. So look at this line here. Passes through the points AB. I suppose you could call AB a line segment on the line. The line will continue on into infinity. You couldn't draw another line through those 2 points. You couldn't draw a line this way or which way would it go. You need at least 2 points. So basically what it's saying is there is exactly 1 line through any 2 given points. And that's all you have to accept. In other words, we can draw only 1 line through points A and B. And we can't draw another line through those. Be on top of it. And that doesn't make sense. Axiom 2 then. It's the ruler axiom. Okay, so the ruler axiom, the properties of the distance between points. So this axiom has the following properties, okay, and you need to take these down as part of axiom 2. The distance between 2 points is never negative, okay? So we would never measure something, a line, and say that it's minus 3 centimeters. Like anything, if we're measuring like the area of something, it's never negative. It's always going to be positive, right? So that's one key point. The distance between 2 points is never negative. Point 2, the distance between A and B is the same as the distance between B and A. So that is, and we've come across this already, remember in one of your questions, that the length of AB is equal to the length of BA, right? Remember those straight brackets mean length, okay? So, or the distance. Length and distance mean the same thing. So the distance between point A to B is the same as B to A. You can say that they're the exact same as each other. So if AB is equal to 5 millimeters, then BA would also be equal to 5 millimeters. Then point C, or part 3, sorry. If point C lies on AB between A and B, then we can say that AB is equal to AC plus CB. So the whole length AB would be equal to the length from A to C plus the length from C to B. So say for example we said that AB was equal to 10 centimeters and AC was equal to 4 centimeters. Okay, then CB is going to be 6 centimeters, isn't it? Let's have a little diagram to show what we mean, right? So remember we said AB was 10 centimeters altogether. And we said that A to C was 4 centimeters. So remember we confirmed that. So remember we said that line AB was equal to 10 centimeters and A to C, we said up here that AB is equal to AC plus CB. So say if we're given A to C being 4 centimeters, then we can easily work out C to B by taking 4 away from 10, and that gives me 6 centimeters. So therefore we can say that AB is equal to AC plus CB. Okay? And then the last point then, that given any ray, so remember a ray is a line that starts at 1 point, continues through another point and goes on into infinity. From the point A, and given any real number k being greater than 0, there is a unique point B on the ray whose distance from A is k. So for example, we can mark off a distance of 5 centimeters on a ray, okay, from a point A and call this point B. There is no other point on the ray that is 5 centimeters from A. So AB is equal to 5 centimeters, okay? So look at this here, right? Remember, a ray starts at 1 point, continues through another point and on into infinity. So given any ray from the point A, that's the starting point, and given any real number k, there is a unique point B on the ray whose distance from A to B is equal to k. K can be any kind of real number. Real number, remember, is any number that's on the number line, but like a measurement. So we can mark off a distance of 5 centimeters on a ray from a point A and call this point B. Okay? Okay, and the third axiom is axiom 3, which is angles on a line, which you've come across already, right? So you just take down angles on a line that we accept. So what we do is we accept that when we have a vertical and a horizontal line and they meet, we have right angles on either side, okay? So we accept that, right? We don't have to prove that. The lines are said to be perpendicular to each other, okay? Why is that not continuing on? This angle is also a right angle, and this explains why the angles on a straight line add to 180. So that's axiom 3, that the angles on a straight line add to 180. We do not need to prove it, it's just we accept it. Angles on a straight line add up to 180. So let's look at what we have here. We have A plus B is equal to 180. Remember, this is called a supplementary angle as well. So say, for example, angle I don't know, we could just say one of the angles is 70 degrees. What would angle B be? We could get that by taking it away from 180. That would give me 110. Say if we said that angle here was 35 degrees, which is an acute angle here, isn't it? If you take that acute angle away from 180, what is the value for x then? 145, because remember, it's straight angle. This whole thing is a straight angle. Just because it's divided by something here, a line, the whole thing would add up to 180. Okay, so find the unknown angles here, right? So I'm going to let you take those down as examples and find them yourselves, okay? So I'm not going to go through those answers. I want you to find them yourself, okay? As questions, you can put them in. As part of axiom 3, we have angles at a point as well. So you have angles on a line and angles at a point. So angles at a point then. So remember, angles on a line add up to 180, right? So that's on a line, because that's just one line here. But say we add up or we continue the vertical line through, we have angles at a point here. So these are all angles at a point. There's a point here. So what can we say? That this diagram helps us explain that why angles at a point add to 360 degrees, because they all create 90 degrees on either side, and 4 90s would be 360, okay? So we can see that they can be drawn in various different ways, look, but all of those angles would add up to 360 degrees because they're angles at a point. So that's your next point to put in for axiom 3. Angles at a point add up to 360 degrees. So let's look at some real life straight lines, I suppose, or angles on a line. We've got T-junctions that you meet, if you're going in the car with your family members. We have angles at a point then, right? So which form 360. So we've got crossroads. So when you meet a road, maybe like where you're living, and you have to stop and there's cars coming towards you or cars coming from you on either side, or you're out on your walk and you come across like a pathway where there's 4 different paths, they create 360 degrees. So angles at a point, we can say that A plus B plus C plus D equal to 360 degrees. Okay, so this is just working out. So how would we work out angle A here? So if we know that all angles add up to 360 degrees, how would we work out A? So we would just add up 85 plus 80 plus 75 and take it away from 360, and that would easily get me angle A. 120 degrees then, okay? So I'd like you to work out this one yourself. And the last axiom then that you take down. So I know it says axiom 5 because we don't do axiom 4 yet. We do axiom 4 next year. So axiom 1, axiom 2, axiom 3, axiom 5. So axiom 5 is the axiom of parallels. And what it says that given any line K and a point P, okay, so remember, given a line K, we call the line K, and a point P in it. So see, the point is always marked by a capital letter and the line is always marked by a lowercase. There is exactly one line through P that is parallel to K. Okay, so what it's saying is we have a line K, and say we have a point P up here. There's going to be exactly just one line that would pass through P and that would also be parallel to K, and it's equidistant from it. Okay, so we can draw only one line through the point P that is parallel to the line K. So that is your 5 axioms, right? So let me just recap the 5 axioms, and you must take these down. So axiom 1 is the 2 points axiom, okay? Axiom 2 then is your ruler axiom, which has 4 different characteristics, 4 different characteristics, I suppose, you can take down here. So that's a long one, right? Then axiom 3 is the angles on a line. and it's also angles at a point, okay? We accept these with our proof, so we can see there's various different ways. And then axiom 5 then, so just a few examples to take down and try that example yourself. Then axiom 5 then is the axiom of parallels. So where you have a line K and a point P above it, and there's exactly one line through P that is parallel to K. So those 4 axioms need to be taken down and learned, okay?